Let's look at spectroscopy and Beer's law. Looking at these test tubes down below, how do you know which one is the most concentrated? And the answer to that is this darker one. Would this technique work with all solutions? And the answer is no. This only works for colored solutions. The darker the color, the more concentrated the solution is. If I had something that was clear and colorless like salt water, there'd be no way just to look at it to see if it was very concentrated or just mildly concentrated. I would have to do more chemical testing. But in the lab, there is a way to analyze without altering the solution what a colored solution concentration would be. So why does the color fade as the concentration is lessened? The concentration is the number of moles that's dissolved in your solution. More molecules or more ions that are dissolved means more light is caught. And we can use something called Beer's law. Beer's law quantifies the relationship between color and the concentration. You take your sample solution and you put it into a spectrophotometer or a colorimeter, and you're able to measure the absorbance of light that is passed through the solution. On your data sheet, this is Beer's law right here. That little epsilon sometimes is written as a lowercase a. It just kind of depends on the year for the AP College Board. But that epsilon, that capital epsilon Greek letter, that is molar absorbance. B is the path length, which would always be 1 centimeter, and C is the concentration. If this is set up according to our y-intercept, if you put absorbance on the y-axis, your slope is going to be that molar absorbance right there. And then on X, that will be your concentration. Your y-intercept of B, if you always start with your line at 0, then you can just ignore that part of this y-intercept equation. So again, absorbance is going to be on the y-axis, concentration is going to be on the x-axis, the slope is that molar absorbance. And again, this will only work with colored solutions. So solutions that have as their cation a transition metal, so copper or cobalt or iron, all of these have colored solutions, and so you can see that the darker the color, then the more concentrated it is, the lighter the color, the less concentrated it is, and that's because solutions that have a higher molarity will absorb more light. Now, what wavelength of light should we send through a solution? Well, we want to send a wavelength of light that will be the most absorbed. That way we can get really good data. So you're going to use a machine called a spectrophotometer, and it's going to analyze all the wavelengths. So it will send all the wavelengths to the solution, and then it will give you a little graph just like down that's on this slide. And you're going to look at where it peaks the highest, and wherever it peaks the highest, that would be the ideal wavelength to send through a solution to analyze the concentration. Now on this sample that I have on this slide, notice that there's 2 peaks. Either one of those would be satisfactory to send through a solution to analyze what the absorption is. And it is based on the color wheel and the complementary color. So in other words, if I had an orange solution, the complementary color, or the color opposite on the color wheel of orange, would be this blue solution. So I would want to use something, so in between 435 and 500 nanometers would be the ideal for an orange solution. But the spectrophotometer, it is very specific and will give you a specific wavelength that you can use. And again, this one just happens to have 2. Sometimes you only have 1 to pick from. Now in the lab, I have a spectrophotometer, but I don't have one for every group. So we use something called a colorimeter. And the colorimeter only has 4 wavelengths to pick from. And so you just pick the closest wavelength. All right, so what does this mean in the laboratory? It means that if we had different concentrations of solutions, I could calculate their absorbance. And as long as I knew what their concentrations were, I could generate a standardized graph or a standardized curve. And that's exactly what happened here. So I made up some solutions that I knew their known concentrations, and then I put it into my colorimeter and I got specific absorbance points. And then I graphed it. I did a line of best fit, and it's ideal to go through the 0 just because then you don't have any y-intercept. But let's go ahead and redraw this graph. So I would go through the y-intercept, and then I would just go through all those data points and just do the line of best fit. So once I get a standard curve, then I can be given an unknown solution where I don't know what the concentration is, and I can use this curve to figure out what the concentration is. So for example, my unknown, if I put it into my colorimeter and I got my absorbance as 0.6, let's say, then I could read this line and I could say that my concentration for that is 0.1 molarity. So in using Beer's law, you have to have known solutions and then generate a graph. And then when you're given an unknown, you just read the concentration off the graph. And again, in Beer's law, this epsilon, that's the slope. So if we ever really needed to find the molar absorbance, we could calculate the slope, which is rise over run. How much it goes up divided by how much it goes across. So here's a Beer's law problem. This is a sample problem from an exam. So number 1, it says the absorbance of an unknown solution is 0.4. What is the concentration? And they give you this graph. Look at your absorbance 0.4, which is right here. And I'm just going to draw a line across. And I'm going to read it down. So I'm going to say it's just past 0.2 molar concentration. So I'm going to say 0.21. As long as I'm close, I'm going to get the credit. Question 2 says Beer's law as an expression includes 3 factors that determine the amount of light that is absorbed. Name the 3 factors. I know that the Beer's law formula is absorbance equals the molar absorbance times B times C. And so I would say that B would be the path length, and that's always going to be 1 centimeter, and that's because that's the size of our little cuvettes that we use in the lab. C is going to be concentration, and then that epsilon is going to be the molar absorbance. So that would be naming the 3 factors. And then 3, describe how a spectrometer or a spectrophotometer or a colorimeter, how it works. Light is shined through a solution that's in a cuvette, and then the absorbance is measured. Again, the absorbance is how much of the light that is absorbed by all the ions that are in solution. There are lots of different types of spectrophotometry. The type of spectrophotometry that studies this transmission or reflection of different frequencies of the electromagnetic spectrum is what we're looking at it. There's different types. There's infrared and there's UV ranges that can be looked at. And usually they're looking at a solution. For us, we're just using the visible light region. Other types of spectroscopy, there's atomic absorption spectroscopy, atomic emission spectroscopy, mass spectroscopy, and we've studied some of these in the past. Nuclear magnetic resonance, that's more research-based. A spectrophotometer, again, measures absorbance or transmittance. In our lab, it measures absorbance. The sample is placed in a little cuvette. The light of the particular wavelength is selected. That will give the maximum absorbance, and that's shined through the sample. And here's a picture of how it all works. So again, that light wavelength is specified. It's shined through the cuvette, and then you get your data outputted.